Hey everyone, welcome to another video. We're looking again at the sine rule today, and we have defined this particular formula from the last video. A over sine A equals to B over sine B equals to C over sine C. So just a little recap, if we have a triangle here, and I have, for example, an angle of C, a side C, angle of A, a side A. Now, these are just placeholders for any side lengths or angle lengths. We don't have to do A, B, and C, but this is just a way to visualize this. So what our sine rule tells us is that the fraction of one side over its opposite, the sine of its opposite angle, so this side, for example, with this angle, is going to be equal to another side, to a different color, B, for example, to the sine of the opposite angle to it, so to this one here, and finally a third side to its opposite angle up here. So we're going to get a lot more practice with this, obviously, with these particular questions, but that's essentially what the sine rule tells us. And we can use this to set up equations and then find lengths of sides or sizes of angles of non-right angle triangles. So let's look at our first example here, and we want to find a missing side here. So we have this guy over here, and I have an angle of 80 degrees, an angle of 75 degrees. I have a side of X centimeters and a side of X meters and 7 meters. Okay, so to set up our sine rule, we want to identify the sides we have and the angles opposite them. So I've got a side of 7, and I've got an opposite angle to that as well, here. And I have another side here, and an opposite angle to it here. So what we're going to do is we're going to use these to set up our sine rule, to set up these fractions and this equation in order to find my unknown side of x. So I can say that x here, my first unknown side, over the sine of the angle opposite it, which is going to be 80. So x over sine 80 is going to be equal to another side, 7, over the sine of an angle opposite to that one, which is 75. That's going to give me x over sine 80 equals to 7 over sine 75. Okay, so now I've got this set up in a way that I have for my sine rule bit up here. So what I'm going to do is I want to isolate the x here. I want to get it on its own. Now here it's dividing by sine of 80 degrees. So we've learnt from equations that we can, if this is dividing by sine of 80, we can multiply both sides by sine of 80, and that is going to give us x on its own. So we want to multiply both sides by sine of 80 degrees here, and that's going to give me that x equals to 7, and here we're multiplying that by sine of 80, a whole number, so that's going to go on the numerator, and that all is getting divided by sine of 75 degrees. So I've used my sine rule equation in order to set up an equation to solve for my unknown of x. I do that by getting the sine of 80 to the other side of the equal sign, and here I end up with approximately 7.1 meters to 1 decimal place. Now, just for a little sense check, opposite sides correspond to opposite angles. So to check that our answer makes sense, because with sine rule there's a lot of calculation errors that can happen, but we do a little sense check. So the 80-degree angle, we would expect the side opposite that one, this one over here, to be bigger than the side opposite a smaller angle. And we expect it to be bigger only slightly, because 80 is only slightly bigger than 75. So we can sense check this and say, well, an answer of 7.1 kind of makes sense, because the bigger the angle, the bigger the opposite side. That's how triangles work. There's this whole compensation idea that we've talked about at length before. But this is how we can solve for an unknown side. And here we're going to do two questions, finding unknown angles, and we're going to talk about something interesting that comes up here, and we're going to link that back to what we did with our obtuse angle trigonometry from the last few videos. So if I have a triangle with length here 9 centimeters and 10 centimeters, and I have an angle of 83 degrees, and I have an unknown angle of theta here. So I want to find this unknown angle. So I'm going to set up my trig ratios again, sine rule ratios. So I have a side of 9, and an angle opposite to that is going to be my unknown angle theta. And a side of 10 is opposite my unknown angle of 83 degrees. So what I'm going to do is I'm going to say that 9 over sine theta equals to 10 over sine of 83. Now, interestingly enough, because these are just fractions and ratios, if I wanted to, a over sine a equaling to b over sine b equaling to c over sine c, we can also say similarly that if we took the reciprocal of both, so if we flipped it, that would also be true. So we can say that, okay, also sine theta over 9 is equal to sine of 83 over 10. Now, you don't have to do this, but it's a little, there's quite a few more steps when you go through solving this particular equation in this form compared to the form you get over here. Now, since these are both fractions, they're both equal, whether I have this as 9 over sine theta equals to 10 over sine of 83, or flipped over, sine of theta over 9 equals sine of 83 over 10, I can get the same thing pretty much. Well, not pretty much, I get the exact same thing. I can write it in two different ways. So I just need to solve this equation now. So I have sine theta divided by 9, so I can multiply both sides by 9. That's going to clear this denominator here, leaving me with sine theta on its own. And 9 is getting multiplied to both sides, so it will get multiplied up on the numerator here. So we have 9 times sine of 83 over 10. And now I want to get to theta at the end of the day, don't I? I've got an expression for sine of theta, but I want to get to theta. So I can take the inverse sine to find the angle. So I want to take the inverse sine of both sides. So that'll leave me with theta, and I get this thing here. We've talked about this at length before in earlier trig. So I'm taking the inverse of sine in order to get rid of the sine next to my theta. And I get 10 on the denominator here. So when I put this into my calculator, I'm going to get an angle value of about 63.3 degrees. Now, let's pause for a minute. Something weird kind of happens with the sine rule. And this is what's called the ambiguous case. Now, we're going to talk about this a lot in later trigonometry, but it's not as relevant to this question, but we're going to test this out for this question and the following one as well. Now, remember from our obtuse angle videos, when we looked at this unit circle here, we said that the sine of the sine of theta, sine of some angle theta, is also the same value as the sine of another angle, which is 180 minus theta. So the obtuse idea here. So, interestingly enough, because we're using the sine ratio, there's a really weird thing that happens. Because we can say that sine theta, based on the trig identity we defined in the last few videos, this is the same as sine of 180 minus theta. So, I've gotten this answer here because for non-right angle trig, it's possible for me to have obtuse angles as well. When we looked at right angle triangles, we were confined to, because this angle was 90, both of these were going to be acute. But now we're looking at non-right angle triangles. So it's possible to have an obtuse angle. So as a result, we can say that not only can this angle be 63 degrees, and now this depends on the triangle, of course, and we're going to see why this is relevant for this particular question. We can say this is 63 degrees or 180 minus 63.3 degrees. Or in other words, 116.7 degrees. Now, remember, this depends on context, so let's just look at our triangle again. Now, 63.3, this acute one, it's always going to be a factor. It's always going to be a possible solution. The obtuse one may sometimes, or it may not be. And that depends on the other angles we're given. Now, if this angle size is 83 degrees, then that means if say the theta was an obtuse angle, then let's add these. So 116.7 degrees plus 83 degrees. This thing here, you can already see it's adding to a number greater than 180. Now, the angle sum of a triangle can never exceed 180 degrees. So this answer is actually not correct. So once we find a theta value, we have to consider this ambiguous case, but we know whether it exists or it doesn't based on the other angles in the triangle that we're given. Now, we're given an angle that when it adds to 116.7 gives me something bigger than 180. So therefore, this thing is not a solution. So we only have 63.3 degrees as a solution. Now, we're going to see this in full effect in the next question as well, but we need to keep an eye on this trig identity when we work with the sine rule. Because we're looking at possibly obtuse angles now, we have to consider this idea of sine theta equaling to the sine of 180 minus theta. Okay, doing one more question here. We have this triangle here. I have an angle size of theta. I have 40 degrees here. I have 4 centimeters and I have 6 centimeters. Okay, so applying sine rule, once again, I have this side and it is opposite to this unknown angle. I also have this side and it is opposite to this unknown angle. So I'm going to set up my sine rule here. So I'm going to say that 6 over sine theta equals to 4 over sine 40. Now remember, we can also write this as, if we want ease of calculations, we can also say sine theta over 6 is equal to sine 40 over 4. This is the exact same thing, but it may be advantageous of us to use the second one because there's a lot less, the sine theta is on the numerator, so there's a lot less working out and solving the equation here. So if we do this one on the right hand side, we want to multiply both sides by 6, and that's going to give me, because that clears the 6 on the denominator here, I get that sine theta equals to 6 times sine 40 degrees over 4. Now just as a side note, because if you're still not sold on writing this in a different way, we can still solve the left-hand equation here in the same way with the sine theta on the denominator. And I'm actually just going to do that right now, just to show that we get the exact same thing as we did over here. So let's say we solved it this particular way, and I'll rub this out so it's not as distracting. Okay, we want to get the sine theta on its own, but not on the denominator. That's not really helping us here. So we're going to multiply both sides by sine theta to get it on a numerator and sort of eventually making it into something on its own, eventually isolating it. So I can say that 6 equals to 4 times sine theta over sine of 40. Now I can multiply both sides by sine 40 to get 4 sine theta on its own. So multiplying this clears my denominator here, and I'm left with 6 times sine 40 equals to 4 sine theta. And hopefully you can kind of see what's happening now. I'm dividing both sides by 4 to get me to sine theta on its own, and I'm left with sine theta on one side equals to 6 sine 40 over 4 on the right hand side. And that's exactly what we got down here. These two are exactly the same. But you can see, using the first one like this, it's a lot of work to get to sine theta. We can just, to make this easier for us, flip these over, take the reciprocal of both sides, and get something like this. And it's only one step to solve the equation. Okay, now that we've gotten here, I want to get to theta by taking the inverse sine of both sides, leaving me with theta on the left equaling to 6 sine 40 over 4. And putting this into my calculator, I'm going to get 74.6 degrees. Now, remember, for possibly obtuse angles, I can have this relationship here when I use sine. That the sine of some angle theta, it's going to give me the same answer, the same ratio for another angle of 180 minus that theta. So my second answer, I can have 74.6 degrees or 180 minus 74.6 degrees. And that's going to give me 105.4 degrees. So I have two solutions here. I have 74.6 or 105.4 as an answer. And that is using this thing that we observed here. When we have the possibility of obtuse angles, there is a particular trig identity that we have to consider. Now let's just check if that works here, because my angle here is 40, both of these answers work. Because if I added 105.4 to 40, I would get something less than 180 degrees. Or if I added 74.6, I'm obviously again going to get something less than 180 degrees. But for this particular question, I can have two possible angle values. And this is based on something we will look at a bit later called the ambiguous case. We'll explore this a lot. Later in year 11 trig. We'll talk about this a lot more at length. But for now, based on the trig identity that we've looked at in the past, we can say that not only can we have one angle value, but depending on the context, depending on our given angle of 40 degrees here, we can have two possible values of theta. But that brings us to the end of the video. Thank you so much for joining me, and I'll see you next time.